All right, our next speaker is a first-time CAMLIS participant, and in fact, this is his first conference at all, so I'm very excited for him to get the warm CAMLIS welcome that I know we always provide. This is Tirth Patel. He's going to be presenting small effect sizes in malware detection, make harder train test splits. So I will pass it off to Tirth.
Thank you, everyone. My name is Tirth Patel, and I will be presenting small effect sizes in malware detection, make harder train test splits. I would like to thank Booz Allen Hamilton, UMBC, and LPS for their support in making this work a success. Moving on, so the slides are organized as we first go over the challenges we face due to the data in the malware detection and what motivated us to put significant effort in this research. We go over our methodology and approach on how we are tackling this solution problem, and then we move over to the results we got from applying our approach to different models. And we would like to conclude on saying the justification of our work. And lastly, we will discuss the limitations and the future work which can be carried off from this. So, starting the machine learning is being used in malware detection for quite some time. Both industries and academia are heavily researching in this field for quite a few years. So industry trained models are normally come in contact with hundreds of millions of files every day. They are very much concerned with the minute changes of performance in the model. Even a change of 0.1% in the model's performance can lead to hundreds of thousands of files, either inaccurately classified or correctly classified. But there is a problem in the data discrepancy in the academia and the industry. So while the academia is also researching that models, they are making models every day, but when these models are transferred to the industry everyday data set, they tend to not perform very well. And the reason is the industrial models are trained mainly on tens of millions of files, whereas the academic researchers use tens of thousands of files. And the problem here is the lack of publicly available data sets for the malware detection. There are numerous reasons: licensing, proprietary issues, cost, storage, etc., due to which the public data sets are not available readily, and that does not help the academic research create models which are better suitable for the industry standards. So the objective of our work would be to have a ways to create a data set which can be used by the academic. So that they can evaluate their models in a better way, and not by increasing the data, not by increasing the training test data, anything like that. We will keep the data set size considerably smaller, but still have a way where the academics can still evaluate their model's performance. So we will be creating the data set by using the weaker model. Actually, weaker models would be used to create this train test data set. And those data sets will be used to evaluate the performance of the stronger models. And the data sets we will create would have difficulty levels. We will not be creating a data set which is simply too challenging or simply too easy for the models. We want to create a data sets of different levels of difficulty, so that while evaluating the performance of the models, we can get accurate results on the statistical test. So a malware classifier has to be robust enough. It has to identify the files which are unseen. It has to generalize on the unseen data. So the key insight of our train test split would be we will limit the bias problem which arise due to the malware files of the similar families in the test set. So our training set and the testing set in our splits will not share the samples belonging to same malware family. And we will also make sure that the data sets we create are of varying difficulty levels so that we can evaluate the performance of the classifiers in a more better way. So before we go any further, let's look at the data set we are using. So we got our malicious data set from the virus share. We took the 184 prominent families from the virus share, which are labeled from the AV class. So total, we have 10,000 malicious files for each of the 184 families, which we split into two parts. 8,000 we will be using for training purpose and 2,000 we will be using for testing purposes. We got the benign files from the Ember dataset. We are using 300,000 files for training and 100,000 files for testing. So the first step in creating the data splits was we want to see how each malware family is doing across all the other malware families. So for that, we pick samples, 8,000 samples from a single malware family, match it with 8,000 benign samples, train the malware classifiers, and predict it across each of the 2,000 samples of all malware families. So we get a recall vector of say 1 cross 184, and basically we repeat this step for each of the 184 malware families. You end up with a data matrix of 184 cross 184, which tells you how each malware family will perform across all the rest of the malware families. So this is the heat map for the Malcolm GCT classifier, which we used. Okay, sorry for we cannot see the index. So basically, I will tell you the white the white cells represents where the recall value is extremely high, which will be near about 1. And the darker the column goes, it shows you the recall value is very low, approximately 0. So in here, each cell will tell you when the Malcolm GCT was trained on the row family and how it performed on the column cell family. So we can see the diagonal line, which is generally white, which shows that yes, the classifier is performing extremely well on the samples belonging to same families. We see the horizontal black lines, which represent that certain families are not good for training. They do not identify most of the families except themselves. We see the vertical black lines, which represents that no matter what family you use for training the models, they are not going to be identified or predicted except for themselves. So from this data matrix, we have devised algorithm, which we call it as benchmark search algorithm, to basically create data sets, which will be used as a benchmark to evaluate the malware classifiers. So we have the input of the 184 cross 184 matrix. We have a target recall threshold tau, so which will identify how difficult the train test split of the data set we want. So if we give a lower value, lower target recall, so we will get a harder train test split. And if we give a higher recall value, we get an easy train test split. And so we simply have input the target threshold we identify the elements which are very close to the target threshold in the matrix. We randomly pick those cells and we create a training and testing data set, but we make sure that no families in the train and test set are similar. We do not want the same families existing in the train and test split. And at the end, we get with a set of training and testing set. And we are limiting our set to size 10. So each train test split will have 10 malware families for training and a set of 10 malware families for testing. Yeah. So this is the overall view of how we are generating the train test split. And we have 3 categories. So the recall value, as you can see over here, we are using 3 different recall value, which is 0.25, 0.5, and 0.9. So the higher means it's an easy split. So as you can see here, so what do we mean by easy? It's that when we use the samples from the training data set and we train the model and we use to predict the samples in the test set, we get a recall value of around 0.9. This is just a theoretical value which we obtain from the graph. Actual training results might be different, but yes, that's how we say that, okay, the split we obtained was easy, medium, or hard. And notice the important thing is the splits do not share the same family in the training and testing, but 2 split might share a same family. There may be some families common in 2 different split, but in a split, there are no common families for train and test. Yeah. So now that we obtained total of 30 splits, we got 4 malware classifiers, which are byte engrams, Malcolm GCT, and the XGBoost model. We train and test the results on each of the splits and average it accordingly in their category. And we can see the results for easy, medium, and hard. And there is also a normal category. The normal category is basically when we randomly sample the files for the training and testing set, which are of the similar size as our train test split. These models generally give the accuracy which is greater than 90%. They are all considerably very good classifiers in predicting the samples. But from these results, we can see that we used the Malcolm model for generating our splits, which was a considerably weaker model than the XGBoost. But the splits we got, as we can see, the hard split was able to bring down the XGBoost model's high accuracy from 99% to 72%, which tells us that we can evaluate the improvements in the XGBoost model with the harder splits. With normally, to see the small improvements in XGBoost, you have to give out about millions of files to even see the improvements in the XGBoost model. But now we can have the harder splits and see the improvements with the small data set. And we can also see the consistency for each of the easy, medium, and hard data set across all the 4 models we trained and tested. So this is how the split. We have the Malcolm GCT classifier where we display the results of each of the split we got. So the red determines all the hard splits, the blue tells all the medium splits, and the green is all the easy splits. You can see how they are grouped among themselves, but there is also consistency among each of the splits. We want that consistency because we do not want our data sets to be lying on the hard end. Either they are too easy or just too difficult for the models, then we won't get good statistical results across the various models if we just create too much hard or too much easy splits. So to conclude our approach, I would say, yes, we were able to successfully generate the train test splits, which from the weaker model to evaluate the stronger models. We can distinguish the performance of the stronger models by using the different levels of split difficulty. They can and I would like to go over the limitations and the future work for this. So we only used the 184 malware families out of tens of thousands of malware families out there, which is a considerably a small fraction of it. We also used only 4 models out of there are lots of malware models available. We tried to limit the bias from the data arise due to the data, but in generating the train test split, there might be bias from the algorithm selected itself. For example, if you use the XGBoost model for creating the train test split, we might end up with too much hard split, which the other models might be not able to generalize well over the hard splits, which tends up to screw the evaluation results from them. Also, certain combinations of malware families tends to sometimes boost the model's performance or sometimes lower the model's performance. Do not know the reason why that's happening, and that might be the area of interest for the research. So before the ending, I would like to go over some of the approach we used for generating the train test splits, which did not work out. So one of the approach was to use the top K families pick from the 184 cross 184. So we basically average across all the rows in the matrix. We sort it in the descending order, pick out the top K families, and train the malware classifiers on top K families, and basically use to predict on all 184 malware families and see how that will work. So we used a K for top 5, 10 till 35. And this is the result. As you can see, the recall generally lies between 0.7 to 0.8. By adding some families, we can see the performance drop, and sometimes you see the performance increase. Yeah, but adding too much families also does not increase the model's performance by a considerably large number. And this is how the top 5 families performed on each of the 184 families. As you can see, the average recall was around 0.7, but there is too much variance in this data. If we try to create the data sets from it, we would either end up with too high recall values or too low recall values. We do not want either of them. We want to create splits which are of considerably, we can scale the difficulty level. We do not want the train test splits on too much of the hard ends. And we tried the worst case families approach, which was basically to get the average across the rows for the data matrix, sort it in ascending order, and pick the top families, which will give you the worst performing families. And you train the classifier on it, and you predict it on all 184 families. So this is the result we get for the worst 10 families pick. As you can see, only the same families are identified by the models trained on it. The model completely overfit on the same malware family sample. It did not work for any other families, and it's not good for creating our train test data splits. So thank you so much.
All right, thank you so much, Tirth. All right, we have time for a couple of questions, I think. We already have a few coming in on the Slack channel. So I'll start with one where someone's asking if you can elaborate a little bit more on what you're defining as a malware family. So maybe a little more background on the AV class definition of malware family.
So the AV class is a tool which labels your malware files. It categorizes into the different malware families. I guess I don't remember the approach it takes, but it basically gives you list, and I guess it uses the popularity approach or something, and it labels them into the malware families. And it's basically a class given to a family. We organize the samples into different families based on their shared attributes or characteristics.
Thank you. And Jennifer is asking, did you do hyperparameter tuning for each train test split?
No, that's also one thing. This research basically takes a lot of time. The models which we use, some of the models were using neural networks, and to train and test the models on this size, it requires a lot of computation powers. And that is also a limitation in this approach. If we try to increase the number of families or number of samples, it runs for a long time. But we went by what the Malcolm GCT Ember, they have their code available. We picked the same parameters which they had. We did not apply the tuning from our side.
Okay, so one, I think I would say comment, maybe you can respond to the comment, but it's also related to a question I had about, so Sarah is asking about the heat map that you represented there, showing the correlate, or not the correlation, but the recall for each combination of the splits. And she's saying that it would be interesting to see it represented as a graph and that you might see some interesting structure there. I was curious, for the ones where you do see kind of like across the board successful ability to classify, were you able to do any digging with subject matter experts into what the family is, or hypothesize about any data artifacts that might have made it more easy to classify regardless of what the training set was?
No, I did not look into that, but yes, that is certainly which I might look into it.
And we'll do one last question here. Let's see. So Sven is asking, what about the performance of the model trained on the normal split evaluated on the hard splits test set? I'm not sure if I've, I think Sven's here, so he can elaborate. Yeah. Do you want to run back there? He's at the very back. Sorry. Okay, great. And Adrian just posted a link to AV class on the Slack.
So I'm guessing there were some models, some malware families that are in the test set of the normal split and the hard split. I was wondering if the normal split generalizes better to those some malware families in the test set of the normal split, normal data, and the test set of the hard data. I wonder now if the normal set generalizes better to those new families versus the hard set generalizing, like how. Yeah.
So the normal is not a split, it's the randomly sampling of the data from our data set. It was not a split. Yeah, the splits were only the hard, medium, and easy.
Okay, sorry, that explains it.
All right, that brings us to the end of this talk. So thank you so much, Tirth. Great job.